What if the universe holds secrets so profound that they could rewrite everything we know about reality? Picture this, a cosmic phenomenon so mysterious that it defies the very laws of physics as we understand them. These are not black holes, but their enigmatic counterparts, white holes. Today, we're diving into one of the most fascinating mysteries of space, the enigma of white holes and their existence. From their theoretical origins to their potential role in the fabric of the cosmos, we'll explore 25 specific space mysteries that will leave you questioning the very nature of the universe. Are white holes real? Could they hold the key to understanding the Big Bang, wormholes, or even the multiverse? Stick around, because by the end of this video, you'll uncover mind-bending theories and discoveries that could change the way you see the cosmos forever. Let's embark on this journey together and unravel the secrets of white holes. Now, let's take a closer look at what white holes actually are. Imagine a black hole, but in reverse. While black holes are known for pulling everything in, even light, white holes are theorized to do the exact opposite. They would expel matter and energy, refusing to let anything enter. Think of them as cosmic fountains, spewing out material instead of swallowing it. This idea comes from the equations of general relativity, the same framework that predicts black holes. In fact, white holes are essentially the mathematical mirror image of black holes, emerging as a solution to Einstein's field equations. But here's the catch: while black holes have been observed and studied, white holes remain purely theoretical. No one has ever detected one, and their existence is still one of the biggest mysteries in astrophysics. So why do scientists even consider them? Well, white holes could help explain some of the universe's most puzzling phenomena, like the origins of the Big Bang or the behavior of spacetime itself. They might even hold clues about how information escapes from black holes, a problem that has baffled physicists for decades. Yet, their elusive nature keeps them shrouded in mystery, leaving us to wonder, are they real or just a fascinating quirk of mathematics? As we explore further, you'll see how white holes could reshape our understanding of the cosmos. Now, let's dive into the fascinating mathematics behind white holes. At the heart of this mystery lies Einstein's field equations, the cornerstone of general relativity. These equations describe how matter and energy shape the fabric of spacetime, and they give rise to both black holes and their theoretical counterparts, white holes. While black holes are solutions to these equations where spacetime curves inward, trapping everything within their event horizon, white holes represent the opposite scenario. Here, spacetime curves outward, creating a region where nothing can enter, but matter and energy can only be expelled. To understand this better, think of spacetime as a rubber sheet. A black hole would be like a deep, funnel-shaped dent in the sheet, pulling everything toward its center. A white hole, on the other hand, would resemble a bulge on the sheet, pushing everything away. This difference in curvature is what sets them apart. Mathematically, white holes emerge as time-reversed solutions to the equations that describe black holes. In other words, if you could run the equations backward, a black hole would transform into a white hole. But here's where it gets even more intriguing. While black holes are stable and can form naturally through the collapse of massive stars, white holes are highly unstable. They require conditions that are almost impossible to achieve in the real universe, which is why they remain purely theoretical. Yet, their existence in the equations suggests that they could play a role in our understanding of the cosmos, particularly in scenarios like the Big Bang or the behavior of spacetime at its most extreme. So, while we may not have observed a white hole yet, the mathematics behind them offers a tantalizing glimpse into the strange and beautiful possibilities of our universe. As we continue to explore, these equations might just hold the key to unlocking some of the deepest mysteries of space and time. Now, let's shift our focus to one of the most mind-bending theories in cosmology, the idea that the Big Bang itself could have been a white hole. This concept flips our understanding of the universe's origins on its head, suggesting that the birth of everything we know might have been the explosive emergence of a white hole. Imagine the Big Bang not as a singular event of creation, but as the outward burst of a white hole spewing matter and energy into the fabric of space-time. In this scenario, the universe didn't just appear out of nothing. It could have been the result of a white hole's natural behavior, expelling everything from a region of space-time that nothing could enter. This idea aligns with the mathematical description of white holes as time-reversed black holes, where instead of pulling matter in, they push it out with incredible force. But what does this mean for our understanding of the universe? If the Big Bang was a white hole, it challenges the traditional view of a singular starting point. Instead, it opens the door to the possibility that our universe is just one part of a much larger cosmic structure. Some scientists speculate that white holes could be connected to other regions of space-time, or even other universes, suggesting that the Big Bang might not have been the beginning of everything, but rather a transition point from another state of existence. This theory also raises questions about what existed before the Big Bang. If a white hole was responsible, could there have been a black hole in another universe that collapsed and gave rise to ours? The idea ties into broader concepts like the multiverse, where our universe is just one of many, each potentially connected through these cosmic gateways. While this remains a speculative idea, it's a powerful reminder of how much we still have to learn about the cosmos. The notion that the Big Bang could have been a white hole not only reshapes our understanding of the universe's origins, but also invites us to think beyond the boundaries of what we currently know. As we continue to explore these mysteries, the connection between white holes and the Big Bang might just be the key to unlocking some of the deepest secrets of existence. Next, we'll explore how white holes might be linked to another fascinating cosmic phenomenon, wormholes, and the possibility of them serving as gateways to other parts of the universe or even other dimensions. Now, let's venture into another captivating idea, the connection between white holes and wormholes. These two cosmic phenomena might seem like science fiction, but they're deeply rooted in the equations of general relativity. If white holes are the theoretical opposites of black holes, spewing matter and energy outward, wormholes are often imagined as tunnels through space-time, potentially connecting distant regions of the universe or even entirely different dimensions. So, how do white holes fit into this picture? Some theories suggest that a white hole could be one end of a wormhole, acting as an exit point for matter and energy that enters through a black hole. Imagine a black hole in one part of the universe pulling in matter and a white hole in another expelling it. The two could be connected by a wormhole, creating a cosmic shortcut through space-time. This idea isn't just fascinating, it could revolutionize our understanding of how the universe works. But here's where it gets even more intriguing. If wormholes exist, they might not just connect different places in our universe. They could also serve as bridges to other universes entirely. This ties back to the multiverse theory, where our universe is just one of many, each with its own unique laws of physics. A white hole, acting as the exit of a wormhole, could be the doorway to these alternate realities. Of course, this raises some big questions. For one, how stable would such a wormhole be? According to current theories, wormholes would require exotic matter with negative energy to stay open and traversable. Without it, they'd collapse almost instantly. And then there's the issue of actually traveling through one. Even if wormholes exist, the journey might be anything but smooth, with extreme gravitational forces and the potential for time dilation making it a one-way trip or worse. Still, the possibility of white holes and wormholes working together as cosmic gateways is a tantalizing idea. It challenges us to think beyond the limits of our observable universe and consider the vast, interconnected nature of reality. While we don't yet have the technology or evidence to prove these theories, they inspire us to keep exploring, pushing the boundaries of what we know. Next, we'll dive into the challenges scientists face in detecting white holes and why they remain one of the most elusive mysteries in the cosmos. Now, shifting our focus to the practical side of this cosmic mystery, let's explore the challenges scientists face in detecting white holes. Despite their fascinating theoretical foundation, white holes remain one of the most elusive phenomena in the universe. One of the biggest hurdles is the complete lack of observational evidence. Unlike black holes, which we've detected through their gravitational effects and the radiation they emit, white holes have yet to leave any detectable trace in the cosmos. This absence of evidence makes them incredibly difficult to study, let alone confirm. Another major challenge lies in the limitations of current technology. Our telescopes and detectors are designed to observe phenomena that emit energy or interact with their surroundings in measurable ways. But white holes, by their very nature, are theorized to expel matter and energy outward, which might not produce the same kind of observable signals as black holes. Even if they do emit energy, it could be so faint or diffuse that it blends into the background noise of the universe, making it nearly impossible to distinguish from other cosmic sources. Adding to the complexity is the fact that white holes are thought to be extremely short-lived if they exist at all. According to some theories, a white hole might only last for a fraction of a second before collapsing or transforming into something else. This fleeting existence would make them incredibly difficult to catch in the act, requiring instruments with unprecedented sensitivity and precision. Despite these challenges, scientists haven't given up on the search. Some researchers are exploring indirect methods to detect white holes, such as looking for unusual patterns in cosmic microwave background radiation or searching for anomalies in the behavior of known black holes. Others are developing new theoretical models to predict what a white hole might look like and how it could be observed. While these efforts are still in their early stages, they represent important steps toward unraveling this cosmic enigma. As we continue to push the boundaries of our understanding, the search for white holes reminds us just how much we still have to learn about the universe. It's a humbling yet exhilarating pursuit, one that challenges us to think creatively and develop new tools to explore the unknown. Next, we'll take a closer look at how white holes have captured the imagination of popular culture, shaping the way we envision these mysterious cosmic phenomena. Now, let's step into the realm of imagination and storytelling, where white holes have found a unique place in popular culture. While scientists grapple with the theoretical and observational challenges of white holes, filmmakers, authors, and creators have embraced these cosmic mysteries as a source of inspiration. White holes have been portrayed in countless ways across movies, books, and other media, often serving as gateways to other worlds, sources of infinite energy, or even as metaphors for rebirth and transformation. One of the most iconic depictions of white holes can be found in science fiction literature. Authors like Arthur C. Clarke and Isaac Asimov have woven white holes into their narratives, using them as plot devices to explore themes of time travel, alternate dimensions, and the limits of human understanding. These stories often present white holes as enigmatic and awe-inspiring, reflecting the same sense of wonder that scientists feel when contemplating their existence. In cinema, white holes have made appearances in blockbuster films, often depicted as dazzling, otherworldly phenomena. For instance, in some science fiction movies, white holes are shown as portals to distant galaxies or as the key to unlocking the secrets of the universe. These portrayals, while not always scientifically accurate, capture the imagination of audiences and spark curiosity about the real science behind these cosmic mysteries. Television series have also explored the concept of white holes, sometimes blending science with fantasy to create compelling narratives. Shows like Doctor Who and Star Trek have featured white holes as central elements of their storylines, using them to drive character development and explore philosophical questions about existence and the nature of reality. These depictions often simplify the science for dramatic effect, but they also introduce viewers to the idea of white holes, encouraging them to learn more about the real theories behind them. Even in video games, white holes have become a popular theme. Games like Mass Effect and No Man's Sky incorporate white holes as part of their expansive universes, allowing players to interact with these phenomena in imaginative ways. These interactive experiences not only entertain but also educate players about the possibilities of white holes, blending entertainment with a subtle dose of science education. The influence of these portrayals on public perception cannot be overstated. For many people, their first encounter with the concept of white holes comes through popular media rather than scientific journals. While these depictions often take creative liberties, they play a crucial role in sparking interest and curiosity about the mysteries of the universe. They inspire viewers to ask questions, seek out more information, and even pursue careers in science and astronomy. As we move forward, it's fascinating to consider how these cultural representations shape our understanding of white holes and other cosmic phenomena. They remind us that science and storytelling are not so different. Both seek to explore the unknown and make sense of the universe in their own unique ways. Next, we'll dive into the thermodynamics of white holes, examining how these theoretical objects might behave according to the laws of physics. Now, let's shift our focus to the fascinating world of thermodynamics and how it applies to white holes. Thermodynamics, the study of energy and its transformations, plays a crucial role in understanding these cosmic phenomena. While black holes are known for their ability to absorb matter and energy, white holes present a stark contrast, theorized to expel energy and matter instead. This fundamental difference makes them a unique subject in the study of cosmic thermodynamics. At the heart of this discussion is the concept of entropy, a measure of disorder or randomness in a system. For black holes, entropy is closely tied to their event horizons, the boundary beyond which nothing can escape. The larger the black hole, the greater its entropy. White holes, on the other hand, are thought to operate in reverse. Instead of increasing entropy by trapping matter and energy, they might decrease it by releasing energy into the universe. This reversal challenges our traditional understanding of entropy and raises intriguing questions about the nature of these objects. Energy flow is another key aspect of thermodynamics that sets white holes apart. In black holes, energy is drawn inward, creating a one-way flow that leads to the singularity at the center. White holes, however, are theorized to have an outward energy flow, expelling matter and radiation into space. This outward flow could have significant implications for the surrounding environment, potentially influencing the formation of galaxies or even the distribution of dark matter. One of the most intriguing ideas in this area is the relationship between white holes and the second law of thermodynamics, which states that entropy in an isolated system always increases over time. If white holes decrease entropy by releasing energy, they might seem to violate this law. However, some theories suggest that white holes could be part of a larger system, such as a universe with multiple connected regions where the overall entropy still increases. This idea opens up new possibilities for understanding the balance of energy and entropy on a cosmic scale. Another point of interest is the potential connection between white holes and Hawking radiation. While black holes are believed to emit this radiation due to quantum effects near their event horizons, white holes might exhibit a similar phenomenon but in reverse. Instead of losing energy over time, white holes could theoretically gain energy, further distinguishing them from their black hole counterparts. As we explore these thermodynamic principles, it's clear that white holes challenge our understanding of the universe's fundamental laws. They invite us to rethink concepts like entropy, energy flow, and the very nature of spacetime. Next, we'll delve into the role of quantum mechanics in understanding white holes, uncovering how the strange rules of the quantum world might shed light on these enigmatic objects. Now, let's venture into the intriguing intersection of white holes and quantum mechanics, where the strange and counterintuitive rules of the quantum world might hold the key to unraveling these cosmic mysteries. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, offers a unique lens through which we can examine white holes and their peculiar properties. One of the most fascinating concepts in this realm is quantum tunneling, a phenomenon where particles can pass through barriers that would be impossible to overcome under classical physics. In the context of white holes, some theories suggest that quantum tunneling could allow particles to escape from regions that would otherwise be sealed off by space-time curvature. This idea challenges our classical understanding of how matter and energy interact with these objects, opening up new possibilities for how white holes might function. Another area of interest is the behavior of particles near white holes. Unlike black holes, where particles are drawn inexorably toward the singularity, white holes are theorized to repel matter and energy. This repulsion could create unique quantum effects, such as the formation of particle-antiparticle pairs near the event horizon. In black holes, these pairs are thought to contribute to Hawking radiation. But in white holes, the process might work in reverse, with particles being ejected into space rather than being absorbed. The role of quantum entanglement also comes into play when discussing white holes. Entanglement, a phenomenon where particles become interconnected regardless of distance, could provide insights into how white holes interact with their surroundings. Some theories propose that entangled particles near a white hole might exhibit unusual correlations, potentially offering clues about the object's internal structure or its connection to other regions of spacetime. Additionally, the concept of quantum gravity, which seeks to unify quantum mechanics with general relativity, is particularly relevant to white holes. While general relativity describes the large-scale structure of spacetime, quantum mechanics governs the behavior of particles at the smallest scales. White holes, with their unique properties, might serve as a testing ground for theories that aim to bridge these two frameworks, helping us understand how gravity operates at the quantum level. As we explore these quantum mechanical principles, it becomes clear that white holes are not just theoretical curiosities but potential windows into the deeper workings of the universe. They challenge us to rethink our understanding of spacetime, particles, and the fundamental laws that govern reality. Next, we'll examine the connection between white holes and Hawking radiation, delving into how these enigmatic objects might emit energy in ways that defy our expectations. Now, let's turn our attention to one of the most groundbreaking ideas in modern physics, the connection between white holes and Hawking radiation. Stephen Hawking, one of the most celebrated physicists of our time, revolutionized our understanding of black holes by proposing that they aren't entirely black. Instead, they emit a faint form of radiation, now famously known as Hawking radiation. But what if this phenomenon isn't limited to black holes? Could white holes, their theoretical counterparts, also emit energy in a similar or even more dramatic way? Hawking radiation arises from the strange interplay between quantum mechanics and gravity near a black hole's event horizon. According to quantum theory, empty space isn't truly empty. It's teeming with virtual particles that pop in and out of existence. Near a black hole, one of these particles can fall into the black hole while the other escapes, effectively stealing a tiny amount of energy from the black hole. Over time, this process causes the black hole to lose mass and eventually evaporate. It's a mind-bending concept that bridges the gap between quantum mechanics and general relativity. When it comes to white holes, the story might be even more intriguing. While black holes are known for pulling everything in, white holes are theorized to push everything out. If Hawking radiation is a result of particles escaping from a black hole's gravitational grip, could white holes emit energy in a similar but reversed manner? Some scientists speculate that white holes might radiate energy outward, not as a slow trickle like Hawking radiation, but as a sudden, explosive release. This could explain why we've never observed a white hole. They might exist only briefly, releasing their energy in a flash before disappearing. Another fascinating possibility is that white holes could be the other end of black holes, connected through wormholes or other space-time structures. In this scenario, the energy emitted by a white hole might be linked to the energy absorbed by a black hole, creating a cosmic balance. This idea ties back to Hawking's work, suggesting that the universe might have a way of preserving information and energy, even in the face of seemingly destructive processes like black hole evaporation. The implications of white holes emitting energy are profound. If they exist, they could provide a new way to understand the universe's energy cycles, offering clues about how matter and energy are recycled on a cosmic scale. They might also help us solve some of the biggest puzzles in physics, such as the black hole information paradox, by showing how information could escape from these mysterious objects. As we continue to explore the mysteries of white holes, the connection to Hawking radiation reminds us just how interconnected the universe truly is. From the tiniest particles to the largest cosmic structures, the laws of physics weave a tapestry that's as beautiful as it is complex. Next, we'll delve into the idea of time reversal and how white holes might challenge our understanding of time itself. Now, let's take a step into the realm of time itself, where the concept of white holes takes on an even more mind-bending twist. Imagine if white holes aren't just the opposite of black holes in terms of gravity, but also in terms of time. What if white holes are essentially black holes running backward in time? This idea, known as time reversal, challenges our understanding of causality, the relationship between cause and effect, and opens up a whole new way of thinking about the universe. In the world of physics, time is often treated as a one-way street. Events happen in a sequence and causes always come before effects. But when we look at black holes and white holes through the lens of time reversal, this straightforward view gets turned on its head. A black hole, as we know, pulls everything in, including light, and nothing can escape its gravitational grip. But if we imagine a black hole running backward in time, it would behave like a white hole pushing everything out instead of pulling it in. This suggests that white holes could be the time-reversed versions of black holes, acting as cosmic fountains rather than cosmic drains. This idea isn't just a wild thought experiment. It's rooted in the mathematics of general relativity. Einstein's equations, which describe the fabric of space-time, are symmetric with respect to time. This means that, mathematically, the equations work just as well whether time is moving forward or backward. While this symmetry doesn't necessarily mean time reversal happens in the real world, it does allow for the possibility of phenomena like white holes existing as time-reversed black holes. But what would this mean for our understanding of time and causality? If white holes are truly time-reversed black holes, they could challenge the very foundation of how we perceive cause and effect. For example, in a white hole, events might appear to unfold in reverse order compared to what we're used to. An effect could seemingly happen before its cause, creating a paradox that defies our everyday experience of time. This raises profound questions about the nature of time itself. Is it truly linear, or could it be more flexible than we think? Some scientists have even speculated that white holes could be connected to black holes through wormholes, creating a bridge between the past and the future. In this scenario, matter and energy falling into a black hole could emerge from a white hole in a different time or even a different universe. This idea, while speculative, offers a tantalizing glimpse into how white holes might fit into the larger puzzle of space-time and the universe's structure. As we explore the concept of time reversal in white holes, we're reminded that the universe is far stranger and more complex than we often imagine. these theoretical objects not only challenge our understanding of gravity and space-time, but also force us to rethink the very nature of time and causality. Next, we'll dive into the role of white holes in multiverse theory, exploring how they might serve as gateways to other universes and dimensions. Now, let's shift our gaze to an even grander cosmic stage, the multiverse. If white holes exist, could they be more than just isolated phenomena in our universe? Could they serve as bridges connecting our universe to others in a vast multiverse? This idea takes the mystery of white holes to a whole new level, intertwining them with one of the most fascinating theories in modern physics, the multiverse theory. The multiverse theory suggests that our universe might be just one of countless others, each with its own unique set of physical laws and properties. But how do these universes interact, if at all? This is where white holes come into play. Some scientists propose that white holes could act as gateways or cosmic portals, linking different universes together. Imagine a black hole in one universe pulling matter and energy in, only for it to be expelled through a white hole in another universe. This would create a kind of cosmic pipeline, allowing matter and energy to flow between universes. But how does this fit into the mathematics of the multiverse? In the framework of general relativity, wormholes, hypothetical tunnels through space-time, are often proposed as potential bridges between universes. Interestingly, white holes could be one end of these wormholes. If a black hole in one universe connects to a white hole in another, it could create a stable passageway or Einstein-Rosen bridge between the two. This idea, while speculative, offers a compelling way to visualize how white holes might function within a multiverse. What's even more intriguing is the possibility that white holes could help explain some of the anomalies we observe in our own universe. For instance, certain regions of space exhibit unusual gravitational effects or unexpected distributions of matter that are difficult to explain with our current understanding of physics. Could these anomalies be the result of interactions with other universes through white holes? While this remains a hypothesis, it opens up exciting avenues for further exploration. The implications of white holes in multiverse theory are profound. If they do serve as bridges between universes, they could fundamentally change our understanding of reality. They might offer a way to test the existence of other universes, providing indirect evidence for the multiverse. Moreover, they could challenge our notions of space and time, suggesting that the boundaries between universes are not as rigid as we once thought. As we ponder the role of white holes in the multiverse, we're reminded once again of the universe's boundless complexity. These theoretical objects, whether they exist or not, push the limits of our imagination and invite us to consider possibilities that stretch far beyond our everyday experience. Next, we'll explore another intriguing connection, white holes and dark matter, and how they might help us unravel some of the universe's deepest mysteries. Now, let's turn our attention to one of the most elusive and mysterious components of the cosmos, dark matter. Could white holes hold the key to understanding this invisible force that makes up a significant portion of the universe? The connection between white holes and dark matter is a tantalizing possibility that could shed light on some of the universe's most perplexing mysteries. Dark matter, as we know, doesn't emit, absorb, or reflect light, making it invisible to our current detection methods. Yet, its gravitational effects are undeniable, influencing the motion of galaxies and the large-scale structure of the universe. But what if dark matter isn't just some exotic particle or unknown substance? What if it's tied to the existence of white holes? Some theories suggest that white holes could be sources of dark matter, releasing it into the universe in ways we're only beginning to imagine. Imagine this, a white hole expelling energy and matter into space, but not in the form we're familiar with. Instead, it could be emitting dark matter, spreading it across the cosmos. This would explain why dark matter seems to be everywhere yet remains invisible. If white holes are indeed the cosmic counterparts to black holes, It's possible they could be responsible for distributing dark matter, creating the gravitational scaffolding that holds galaxies together. But how does this fit into the bigger picture? If white holes are linked to dark matter, they could help explain why galaxies rotate faster than expected, and why galaxy clusters behave as if they contain far more mass than we can see. These anomalies have puzzled scientists for decades, and white holes might offer a compelling solution. By acting as conduits for dark matter, white holes could provide the missing piece of the puzzle, bridging the gap between what we observe and what we understand. What's even more fascinating is the potential interplay between white holes, dark matter, and the formation of cosmic structures. If white holes are indeed sources of dark matter, they could have played a crucial role in shaping the universe as we know it. From the earliest moments of cosmic history, white holes might have seeded the universe with dark matter, influencing the growth of galaxies and the large-scale web of the cosmos. This idea not only deepens the mystery of white holes, but also offers a new perspective on the origins of dark matter. Of course, this is all speculative, but it's a hypothesis that opens up exciting possibilities for future research. If scientists can find evidence linking white holes to dark matter, it would revolutionize our understanding of the universe. It would mean that these theoretical objects aren't just curiosities of physics, they are fundamental to the very fabric of reality. As we continue to explore the enigma of white holes, we may find that they hold the answers to questions we haven't even thought to ask yet. With this intriguing connection in mind, let's move forward to another cosmic puzzle, the Fermi Paradox, and explore how white holes might provide a solution to one of the most enduring questions in science: where is everyone? Now, shifting our gaze to one of the most profound questions in science, the Fermi Paradox, we find ourselves wondering, where is everyone? The universe is vast, with billions of galaxies, each containing billions of stars and planets. Statistically, it seems almost certain that intelligent life should exist elsewhere. Yet, we've found no evidence of it. This is the Fermi Paradox, and white holes might just hold the key to unraveling this cosmic mystery. One possibility is that advanced extraterrestrial civilizations have discovered or even harnessed white holes as a means of communication or travel. If white holes are gateways to other parts of the universe or even other dimensions, they could serve as cosmic highways for civilizations far more advanced than our own. These civilizations might be using white holes to traverse vast distances in ways we can't yet comprehend, making their presence undetectable to our current technology. Another intriguing idea is that white holes could act as cosmic filters, preventing civilizations from expanding beyond their own regions of space. Imagine a universe where white holes are scattered throughout, acting as barriers or checkpoints. Civilizations that reach a certain level of technological advancement might encounter these white holes, which could either destroy them or redirect their paths, effectively limiting their ability to colonize the cosmos. This could explain why we haven't encountered any signs of extraterrestrial life. They're either unable to reach us or have been filtered out by these mysterious cosmic phenomena. But there's another angle to consider. What if white holes are not just physical barriers but also informational ones? If white holes emit energy or matter in ways that disrupt communication signals, it's possible that messages from extraterrestrial civilizations are being lost or distorted before they ever reach us. This would mean that even if intelligent life is out there, their attempts to communicate could be swallowed up by the very nature of white holes, leaving us in the dark. And then there's the possibility that white holes are hiding something even more extraordinary. What if they're not just gateways or barriers, but entire civilizations themselves? Some theories suggest that white holes could be the remnants of advanced societies that have transcended physical form, existing as pure energy or information within these cosmic structures. If this is the case, then the absence of detectable life might not be an absence at all. It could simply be a matter of us not knowing where or how to look. While these ideas are speculative, they open up fascinating avenues for exploration. If white holes are indeed connected to the Fermi Paradox, they could provide answers to questions that have puzzled scientists for decades. They might explain why the universe seems so empty, or they might reveal that it's far more crowded than we realize, just in ways we're not yet equipped to understand. As we ponder these possibilities, let's turn our attention to another cosmic enigma, the theory of cosmic inflation, and explore how white holes might have played a role in shaping the early universe. Now, let's take a step back in time, way back to the very beginning of the universe. The theory of cosmic inflation suggests that in the first fraction of a second after the Big Bang, the universe expanded at an unimaginable rate, stretching far beyond what we can observe today. But what if white holes played a role in this rapid expansion? Could these mysterious cosmic phenomena have been the engines driving the early universe's growth? One compelling idea is that white holes, with their ability to expel matter and energy, might have acted as cosmic pressure valves during the inflationary period. Imagine the early universe as a tightly wound spring, packed with energy and potential. As inflation began, white holes could have released bursts of energy, helping to fuel the rapid expansion and shape the structure of the cosmos. This would mean that white holes weren't just passive observers in the early universe, they were active participants, shaping the very fabric of space and time. But there's more to this story. Some theories propose that white holes could have been the remnants of earlier universes, left over from a previous cosmic cycle. If our universe is part of a larger multiverse, white holes might serve as bridges between these different realms, carrying energy and matter from one universe to another. During the inflationary period, these white holes could have injected new energy into our universe, accelerating its expansion and setting the stage for everything that followed. Another fascinating angle is the possibility that white holes influenced the distribution of matter in the early universe. As inflation stretched space, white holes might have acted as cosmic seeds, creating regions of higher density that eventually grew into galaxies and galaxy clusters. This would mean that the large-scale structure of the universe, the vast cosmic web we see today, could have been shaped, at least in part, by the presence of white holes. Of course, these ideas are still speculative, but they open up exciting possibilities for understanding the origins of our universe. If white holes were indeed involved in cosmic inflation, they could help explain some of the mysteries that still puzzle scientists, such as why the universe appears so uniform on large scales, or why certain regions of space are more densely packed with matter than others. As we explore these connections, it's clear that white holes are more than just theoretical curiosities. They could be key players in the story of our universe's birth and evolution. And with that in mind, let's turn our attention to another intriguing aspect of white holes, their potential energy output and how it compares to other cosmic phenomena. Now, shifting our focus to the sheer power of white holes, let's explore their theoretical energy output and how it stacks up against some of the most energetic events in the universe. White holes, by their very nature, are thought to expel matter and energy outward, unlike black holes that pull everything in. This expulsion could make them some of the most energetic objects in existence, if they exist, of course. To put this into perspective, let's compare white holes to quasars, which are among the brightest and most powerful objects in the universe. Quasars are powered by supermassive black holes at the centers of galaxies, consuming vast amounts of matter and releasing energy in the form of intense radiation. But while quasars are fueled by the gravitational energy of infalling matter, white holes would theoretically release energy from their own internal processes, potentially rivaling or even surpassing the energy output of quasars. Then there are supernovae, the explosive deaths of massive stars. A single supernova can outshine an entire galaxy for a brief moment, releasing an incredible amount of energy. But here's the twist: white holes might not just match this energy output, they could sustain it over much longer periods. Imagine a supernova that doesn't fade away but continues to pour energy into space, reshaping its surroundings for thousands or even millions of years. That's the kind of power white holes might possess, but how does this energy output work? One theory suggests that white holes could release energy through a process similar to Hawking radiation, the phenomenon predicted by Stephen Hawking for black holes. While black holes slowly lose energy over time through this radiation, white holes might emit energy in a more dramatic and sustained fashion. This could make them cosmic powerhouses capable of influencing entire regions of space with their energy output. Another intriguing possibility is that white holes could act as cosmic batteries, storing energy from earlier phases of the universe and releasing it in bursts. This would make them not only sources of immense energy, but also key players in the evolution of galaxies and the large-scale structure of the cosmos. Their energy output could help explain why certain regions of the universe are more active or densely packed with matter than others. Of course, all of this remains theoretical, as we've yet to observe a white hole directly. But the idea of such an object, capable of rivaling quasars and supernova in energy output, is both thrilling and humbling. It reminds us just how much we still have to learn about the universe and the forces that shape it. With this in mind, let's turn our attention to another fascinating mystery: how white holes might resolve one of the most perplexing problems in physics, the black hole information paradox. Now let's dive into one of the most puzzling questions in modern physics, the black hole information paradox, and how white holes might hold the key to solving it. The information paradox arises from a fundamental conflict between quantum mechanics and general relativity. According to quantum mechanics, information about the state of a system can never be truly lost. Yet, when matter falls into a black hole, it seems to vanish from the universe, taking all its information with it. This contradiction has baffled scientists for decades, but white holes might offer a way out. Imagine a black hole as a cosmic vacuum cleaner, sucking in everything that crosses its event horizon. Once inside, the matter is thought to be crushed into a singularity, a point of infinite density where the laws of physics as we know them break down. But if information cannot be destroyed, where does it go? This is where white holes come into play. If black holes are the ultimate cosmic sinks, white holes could be their counterparts, cosmic fountains, spewing out matter and energy instead of consuming them. One intriguing theory suggests that white holes could act as the exit points for information that falls into black holes. Instead of being lost forever, the information could be encoded in the radiation or matter expelled by a white hole. This would mean that the information isn't destroyed but rather transformed and redistributed into the universe. In this way, white holes could serve as cosmic recycling centers, preserving the information that black holes seem to erase. Stephen Hawking's work on Hawking radiation plays a crucial role here. Black holes are thought to emit this radiation over time, slowly losing mass and energy. But if white holes exist, they might emit a similar form of radiation, carrying with it the information that was once trapped inside a black hole. This would create a kind of cosmic balance, ensuring that no information is ever truly lost, just transferred from one form to another. Another fascinating idea is that white holes could be connected to black holes through wormholes, forming a bridge between the two. In this scenario, information that falls into a black hole could travel through the wormhole and emerge from a white hole in another part of the universe, or even in another universe altogether. This would not only resolve the information paradox, but also open up mind-bending possibilities for how information and matter move through the cosmos. Of course, all of this remains speculative, as we have yet to observe a white hole or confirm their existence. But the idea that white holes could solve one of the greatest mysteries in physics is both exciting and thought-provoking. It challenges us to rethink our understanding of the universe and the fundamental laws that govern it. With this in mind, let's turn our attention to another captivating mystery: the role white holes might have played in the formation of galaxies and how they could reshape our understanding of cosmic evolution. Now, shifting our gaze to the grand tapestry of the cosmos, let's explore how white holes might have played a pivotal role in the formation of galaxies. This idea not only challenges our current understanding of cosmic evolution, but also opens up a fascinating new perspective on how the universe's largest structures came to be. Galaxies, those vast collections of stars, gas, and dark matter, are the building blocks of the universe, but how did they form? The prevailing theory suggests that galaxies grew from tiny fluctuations in the density of matter after the Big Bang, gradually pulling together under the force of gravity. However, this model leaves some questions unanswered, particularly about the rapid pace of galaxy formation in the early universe. This is where white holes could enter the picture. Imagine white holes as cosmic seeds scattered throughout the universe in its infancy. Unlike black holes which draw matter inward, white holes could have ejected vast amounts of energy and matter into their surroundings. These outbursts might have acted as catalysts, triggering the collapse of gas clouds and accelerating the formation of stars and galaxies. In this scenario, white holes wouldn't just be passive objects, they'd be active participants in shaping the cosmos. One intriguing possibility is that white holes could have provided the initial push needed to overcome the resistance of dark matter, which tends to slow down the clumping of matter. By injecting energy into specific regions, white holes might have created pockets of higher density, jump-starting the process of galaxy formation. This would explain why some galaxies appear to have formed much earlier than current models predict. Moreover, if white holes are connected to black holes through wormholes, as some theories suggest, they could have served as cosmic conduits, transporting matter and energy across vast distances. This could have allowed galaxies to form in regions that would otherwise have been too sparse to support such rapid growth. In essence, white holes might have acted as cosmic architects, weaving the fabric of the universe into the intricate patterns we observe today. Of course, this theory is still speculative, and much work remains to be done to test its validity. But the idea that white holes could have played a role in galaxy formation challenges us to rethink our understanding of the universe's history. It suggests that the cosmos might be far more dynamic and interconnected than we ever imagined. As we continue to unravel the mysteries of white holes, we're reminded that the universe is full of surprises. Next, we'll delve into another mind-bending concept: how white holes might influence our understanding of the arrow of time, and whether they could create loops in the fabric of reality itself. Now, let's turn our attention to one of the most intriguing aspects of white holes: their potential relationship with the arrow of time. Time, as we experience it, flows in one direction forward. This unidirectional flow is what we call the arrow of time, and it's deeply tied to the second law of thermodynamics, which states that entropy or disorder always increases over time. But what if white holes could challenge this fundamental principle? White holes, by their very nature, seem to defy the usual rules of time and causality. While black holes are known for pulling matter and energy inward, white holes are theorized to expel them outward. This reversal of behavior has led some scientists to speculate that white holes might represent a kind of time-reversed version of black holes. In other words, if black holes are the end points of matter and energy, white holes could be their starting points, effectively reversing the flow of time in their vicinity. This idea opens up the possibility of time loop scenarios where events could repeat or cycle endlessly. Imagine a black hole and a white hole connected by a wormhole. Matter falling into the black hole could, in theory, emerge from the white hole at a different point in time, potentially even in the past. This would create a closed loop in space-time, where cause and effect could become entangled in ways that challenge our everyday understanding of reality. Such time loops could have profound implications for our understanding of the universe. For instance, they might provide a way to reconcile the apparent contradictions between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. By introducing the possibility of time loops, white holes could offer a new framework for understanding how the universe operates on both the smallest and largest scales. But how realistic are these ideas? While they remain speculative, they're not entirely outside the realm of possibility. Some physicists have proposed that white holes could exist as remnants of black holes that have undergone quantum tunneling, effectively reversing their behavior. If this is true, it would mean that white holes are not just theoretical curiosities but real, observable phenomena that could reshape our understanding of time itself. As we ponder these mind-bending concepts, it's worth remembering that the universe often defies our expectations. White holes, with their potential to bend or even reverse the arrow of time, remind us that the cosmos is far stranger and more interconnected than we can imagine. Next, we'll explore another fascinating possibility: what might happen if two white holes were to collide, and how such an event could ripple through the fabric of space-time. Now, let's venture into a scenario that sounds like it's straight out of a science fiction novel: the collision of two white holes. What would happen if these cosmic anomalies, which are already shrouded in mystery, were to meet? The implications could be nothing short of extraordinary, reshaping our understanding of space-time and the universe itself. When two white holes collide, the event would likely unleash an immense burst of energy, far exceeding anything we've ever observed. Unlike black holes, which pull everything into their grasp, white holes expel matter and energy outward. If two of these objects were to collide, the resulting explosion could send shockwaves rippling through space-time, potentially creating distortions or even new pathways in the fabric of the universe. One possibility is that such a collision could generate gravitational waves, similar to those produced by black hole mergers but with a unique signature. These waves could carry information about the nature of white holes, offering scientists a rare opportunity to study these elusive objects indirectly. The energy released might also trigger the formation of new structures in space, such as galaxies or even entire cosmic filaments, altering the large-scale architecture of the universe. Another intriguing aspect is the potential for space-time anomalies. If white holes are indeed time-reversed versions of black holes, their collision could create a region where the usual rules of time and causality break down. Imagine a scenario where cause and effect become entangled, or where time loops form, allowing events to repeat or unfold in unexpected ways. Such phenomena could provide clues about the fundamental nature of time itself, challenging our current understanding of physics. But what about the aftermath? After the initial burst of energy, the collision might leave behind a remnant, a new type of cosmic object that defies classification. This remnant could be a hybrid of a white hole and a black hole, or perhaps something entirely new, opening up avenues for further exploration and discovery. The study of such remnants could help bridge the gap between quantum mechanics and general relativity, two theories that have yet to be fully reconciled. While the idea of white hole collisions remains speculative, it's a fascinating thought experiment that pushes the boundaries of our knowledge. It reminds us that the universe is full of surprises, and that even the most outlandish theories can lead to groundbreaking insights. As we continue to explore the mysteries of white holes, we may find that their collisions hold the key to unlocking some of the deepest secrets of the cosmos. Next, we'll shift our focus to another captivating mystery: how white holes might leave their mark on the cosmic microwave background radiation, and what that could tell us about the early universe. Now, let's turn our attention to a cosmic canvas that holds the faint echoes of the universe's earliest moments: the cosmic microwave background radiation. This ancient light, often referred to as the afterglow of the Big Bang, carries with it the fingerprints of the universe's infancy. But could white holes, those enigmatic cosmic phenomena, have left their mark on this primordial tapestry? The answer might just reshape our understanding of the cosmos. The cosmic microwave background radiation, or CMB, is like a snapshot of the universe when it was just 380,000 years old. It's a faint glow that fills the entire sky, and within its subtle fluctuations lie clues about the universe's structure, composition, and history. Scientists have long studied these fluctuations to uncover the secrets of the early universe. But what if some of these patterns were influenced by white holes? One intriguing possibility is that white holes, if they existed in the early universe, could have left distinct imprints on the CMB. As white holes expel matter and energy outward, their intense bursts of radiation might have created localized distortions in the fabric of space-time. These distortions could have subtly altered the temperature and polarization patterns of the CMB, leaving behind faint but detectable signatures. Imagine these imprints as cosmic breadcrumbs, pointing us toward the presence of white holes in the universe's infancy. Detecting these signatures, however, is no small feat. The CMB is already incredibly uniform, with temperature variations on the order of 1 part in 100,000. Any imprint left by a white hole would likely be even fainter, buried within the noise of other cosmic processes. But scientists are nothing if not resourceful. Advanced instruments like the Planck satellite and future missions designed to map the CMB with even greater precision could potentially uncover these subtle anomalies. By analyzing the data for unusual patterns or deviations from the expected background, researchers might one day identify the telltale signs of white holes. Another approach involves studying the polarization of the CMB. Polarization refers to the orientation of light waves, and it can carry information about the forces that shaped the early universe. If white holes generated powerful bursts of energy, they could have influenced the polarization patterns in specific regions of the CMB. By mapping these patterns, scientists might be able to trace the influence of white holes back to their origins, offering a glimpse into their role in the universe's formation. But why does this matter? Beyond the thrill of discovery, understanding whether white holes left imprints on the CMB could provide critical insights into the nature of these mysterious objects. It could help us determine whether white holes played a role in the early universe's evolution, perhaps even contributing to the formation of large-scale structures like galaxies and galaxy clusters. Moreover, it could shed light on the relationship between white holes and other cosmic phenomena, such as dark matter and dark energy, deepening our understanding of the universe's fundamental forces. As we continue to probe the mysteries of the CMB, the search for white hole imprints remains a tantalizing frontier. It's a reminder that even the faintest whispers of the cosmos can hold profound secrets, waiting to be uncovered by those who dare to look closely. Next, we'll explore the philosophical implications of white holes and how their existence challenges our understanding of reality itself. Now, let's shift our gaze from the scientific to the philosophical, where the mysteries of white holes invite us to ponder deeper questions about the nature of reality itself. If white holes exist, what do they mean for our understanding of existence? How do they challenge the way we perceive the universe and our place within it? These are not just questions for physicists, but for anyone who has ever looked up at the night sky and wondered about the grand tapestry of existence. At the heart of this exploration is the concept of causality, the idea that every event has a cause. Black holes, with their inescapable gravitational pull, seem to represent the ultimate end, a point where causality breaks down. But white holes, if they exist, flip this narrative on its head. They suggest the possibility of creation, of something emerging from nothing. This raises profound questions. Could white holes be the universe's way of resetting itself? Do they represent a form of cosmic rebirth, where matter and energy are not destroyed but transformed? Moreover, the existence of white holes challenges our understanding of time. In a universe where white holes expel matter and energy, could time itself flow differently around them? Some theories even suggest that white holes might be time-reversed versions of black holes, hinting at the possibility of time loops or alternate timelines. This idea pushes us to reconsider the linear nature of time as we experience it. What if time isn't a straight line but a complex web, with white holes serving as nodes where past, present, and future intersect? Then there's the question of existence itself. If white holes are real, they force us to confront the limits of our knowledge. They remind us that the universe is far stranger and more mysterious than we can imagine. What other phenomena might exist beyond our current understanding? Could white holes be just one piece of a much larger cosmic puzzle, one that includes dimensions and realities we have yet to discover? These philosophical implications extend beyond the realm of science and into the very fabric of human thought. They challenge us to think differently about our place in the universe, to embrace uncertainty, and to remain open to the possibility that reality is far more complex than we can comprehend. White holes, in this sense, are not just cosmic curiosities, they are gateways to new ways of thinking, inviting us to explore the boundaries of knowledge and imagination. As we reflect on these questions, we're reminded that the pursuit of understanding is as much about the journey as it is about the destination. The enigma of white holes doesn't just challenge our scientific models, it challenges us to expand our minds and rethink what we know about existence itself. Next, we'll delve into how white holes might intersect with the search for extraterrestrial intelligence and whether they could hold clues to life beyond our planet. Now, let's turn our attention to a fascinating possibility that ties white holes to one of humanity's most enduring questions. Are we alone in the universe? Could white holes play a role in the search for extraterrestrial intelligence? This idea might sound like science fiction, but when we consider the unique properties of white holes, it's not as far-fetched as it seems. Imagine for a moment that an advanced civilization, far beyond our current technological capabilities, has discovered how to harness the power of white holes. These cosmic phenomena, with their ability to expel matter and energy, could serve as natural beacons or even communication hubs. If a civilization could manipulate or detect white holes, they might use them as markers to signal their presence across vast distances of space. After all, the energy output of a white hole would be unlike anything else in the universe, making it a potential calling card for intelligent life. But how might this work? One theory suggests that white holes could act as cosmic lighthouses, emitting bursts of energy or radiation in patterns that could be detected by other civilizations. These patterns might not be random but could instead carry encoded messages, much like how we use radio waves to communicate here on Earth. If an advanced species had the ability to control or predict the behavior of white holes, they could use them to send signals across galaxies, bypassing the limitations of traditional communication methods. Another intriguing possibility is that white holes could serve as gateways or meeting points for interstellar civilizations. If white holes are connected to wormholes, as some theories suggest, they might provide a shortcut through space-time, allowing civilizations to travel or exchange information more efficiently. This could explain why we haven't detected extraterrestrial life yet. Perhaps they're using technologies and methods that are entirely beyond our current understanding, with white holes at the center of their interstellar networks. Of course, this raises another question. If white holes are being used in this way, why haven't we detected any evidence of it? The answer might lie in the limitations of our technology. Our current instruments are designed to detect specific types of signals, like radio waves or light. But the energy emitted by white holes could be in a form we're not yet equipped to recognize. It's also possible that these signals are being sent in ways that are intentionally designed to avoid detection, reserved only for civilizations that have reached a certain level of advancement. As we ponder these ideas, it's important to remember that the search for extraterrestrial intelligence is still in its early stages. White holes, with their mysterious and powerful nature, offer a tantalizing possibility for how advanced civilizations might communicate or navigate the cosmos. They remind us that the universe is full of surprises and that the answers to our biggest questions might lie in phenomena we're only beginning to understand. With this in mind, let's move forward to explore another intriguing aspect of white holes, their potential role in bridging the gap between quantum mechanics and general relativity, and what this could mean for our understanding of the universe. Now, let's shift our focus to one of the most profound challenges in modern physics, the quest to unify quantum mechanics and general relativity. This is where white holes might play a pivotal role, offering a potential bridge between these two seemingly incompatible frameworks. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains the large-scale structure of the universe. Yet, when it comes to understanding phenomena like black holes or their theoretical counterparts, white holes, these two theories clash, leaving scientists with unanswered questions. White holes, with their unique properties, could provide a key to resolving this conflict. Unlike black holes, which pull matter and energy inward, white holes expel them outward. This reversal of behavior might hold clues about how quantum effects interact with the curvature of spacetime described by general relativity. Some physicists speculate that white holes could represent a quantum correction to black holes, offering a way to reconcile the two theories. In this view, white holes might not just be theoretical curiosities but essential pieces of the puzzle in understanding quantum gravity. One intriguing idea is that white holes could emerge from the quantum fluctuations near the event horizon of a black hole. According to some interpretations, when a black hole evaporates due to Hawking radiation, it might not disappear entirely but instead transition into a white hole. This process could preserve information that would otherwise be lost, addressing one of the biggest challenges in black hole physics, the information paradox. If this is true, white holes could act as a kind of cosmic recycling system, transforming the remnants of black holes into new forms of matter and energy. Another possibility is that white holes could help us understand the nature of spacetime itself. In quantum gravity, spacetime is thought to be made up of discrete, tiny units rather than being smooth and continuous. White holes, with their explosive energy output, might provide a window into this granular structure. By studying how matter and energy are expelled from white holes, scientists could gain insights into how spacetime behaves at the smallest scales, potentially revealing the quantum underpinnings of gravity. The implications of this are enormous. If white holes can indeed bridge the gap between quantum mechanics and general relativity, they could revolutionize our understanding of the universe. They might explain how gravity works at the quantum level, shedding light on phenomena like the Big Bang, dark matter, and even the ultimate fate of the cosmos. While this remains speculative, the potential for white holes to unlock these mysteries is too compelling to ignore. As we continue to explore the enigma of white holes, we're reminded that the universe is far stranger and more interconnected than we often realize. These cosmic phenomena challenge us to think beyond the boundaries of our current knowledge, pushing the frontiers of science into uncharted territory. With that in mind, let's turn our attention to another fascinating aspect of white holes, their potential role in the ultimate fate of the universe. Now, let's venture into one of the most mind-bending possibilities surrounding white holes, their potential role in the ultimate fate of the universe. The cosmos, as we know it, is constantly evolving, and scientists have long debated how it might end. Could white holes hold the key to understanding this cosmic finale? Let's explore the theories. One of the leading ideas about the universe's end is the Big Crunch. This theory suggests that the expansion of the universe could one day reverse, causing everything to collapse back into a single point. If this happens, white holes might play a crucial role. Some physicists speculate that the immense energy expelled by white holes could counteract the forces driving the collapse, potentially delaying or even preventing the Big Crunch. Imagine white holes as cosmic pressure valves, releasing energy to stabilize the universe in its final moments. On the other hand, there's the theory of heat death, where the universe continues expanding forever, eventually becoming a cold, dark, and lifeless void. In this scenario, white holes could still have a part to play. Their explosive energy output might inject pockets of activity into an otherwise stagnant cosmos, creating temporary bursts of light and heat in an increasingly empty universe. While this wouldn't stop the heat death, it could add a fascinating twist to the universe's final chapters. Another intriguing possibility is that white holes could act as cosmic recyclers, transforming the remnants of black holes into new forms of matter and energy. If this process were to occur on a large scale, it might lead to a cyclical universe where the end of one cosmic era gives rise to the beginning of another. In this view, white holes could be the engines of cosmic rebirth, ensuring that the universe never truly ends but instead undergoes endless cycles of creation and destruction. Of course, these ideas are still highly speculative, but they highlight the profound implications of white holes for our understanding of the universe's fate. Whether they delay the Big Crunch, add complexity to heat death, or enable a cyclical cosmos, white holes challenge us to rethink how the universe might conclude its grand story. As we ponder these possibilities, we're reminded that the universe is full of mysteries waiting to be unraveled. White holes, with their enigmatic nature, continue to inspire scientists and dreamers alike, pushing the boundaries of what we know and what we can imagine. With that in mind, let's turn our attention to another fascinating aspect of white holes, their ethical implications and the responsibilities that come with studying them. Now, as we shift our focus to the ethical implications of white hole research, it's worth considering the profound responsibilities that come with exploring such a mysterious and powerful phenomenon. The study of white holes isn't just about unraveling cosmic secrets, it's also about understanding the potential consequences of that knowledge for humanity and the universe itself. One of the most pressing ethical questions is whether we should even attempt to manipulate or interact with white holes, assuming we ever discover a way to do so. The energy output of a white hole is theorized to be immense, and harnessing it could revolutionize technology, energy production, and even space travel. But with great power comes great risk. What if our experiments inadvertently destabilize space-time or trigger unforeseen cosmic events? The potential for unintended consequences raises serious ethical concerns about the limits of scientific exploration. Another consideration is the impact of white hole research on our understanding of the universe's balance. If white holes are indeed the counterparts to black holes, their study could reveal fundamental truths about the nature of existence. But could this knowledge also disrupt our perception of reality or challenge deeply held beliefs about life, time, and the cosmos? The philosophical and ethical implications of such discoveries are as vast as the universe itself. On the flip side, the benefits of white hole research could be transformative. Imagine a future where we harness the energy of white holes to power entire civilizations, or use their theoretical properties to develop faster than light travel. These advancements could open up new frontiers for humanity, enabling us to explore distant galaxies and potentially even escape the eventual heat death of the universe. But this raises another ethical dilemma. Should we prioritize such ambitious goals over more immediate, Earth-based challenges like climate change or resource scarcity? Moreover, the pursuit of white hole research could lead to significant advancements in our understanding of physics, potentially bridging the gap between quantum mechanics and general relativity. This knowledge could unlock new technologies and deepen our comprehension of the universe's workings. However, it also begs the question of who should have access to this knowledge and how it should be regulated. The potential for misuse, whether through weaponization or monopolization, underscores the need for international cooperation and ethical oversight in scientific research. As we delve deeper into the mysteries of white holes, it's clear that their study is not just a scientific endeavor but also a moral one. The choices we make today about how to approach this research could shape the future of humanity and the cosmos. With that in mind, let's turn our attention to the final frontier of white hole exploration, the technologies and missions that might one day allow us to observe or even interact with these enigmatic cosmic phenomena. As we step into the realm of possibilities, the future of white hole exploration holds immense promise, driven by advancements in technology and our ever-growing curiosity about the cosmos. Imagine a world where cutting-edge telescopes, far more powerful than anything we have today, could peer into the depths of space and detect the faint signatures of white holes. These instruments, equipped with next-generation sensors and artificial intelligence, might one day uncover the subtle distortions in space-time that hint at the presence of these elusive phenomena. One of the most exciting prospects lies in the development of space-based observatories. Unlike ground-based telescopes, which are limited by Earth's atmosphere, these orbiting observatories could provide unprecedented clarity and precision. Missions like the James Webb Space Telescope have already revolutionized our understanding of the universe, but future projects could take this even further. Imagine a telescope specifically designed to hunt for white holes, capable of detecting their unique energy emissions or gravitational effects. Such a mission could bring us closer than ever to confirming their existence. But observation is just the beginning. The real game changer could come from advancements in propulsion technology. If white holes are indeed gateways to other parts of the universe or even other dimensions, the ability to travel to them would require breakthroughs in physics and engineering. Concepts like warp drives, which bend space-time to achieve faster-than-light travel, are no longer confined to science fiction. Researchers are already exploring the theoretical foundations of such technologies, and while they remain speculative, the potential to one day reach a white hole is a tantalizing possibility. Another avenue of exploration involves the development of quantum computers. These powerful machines could simulate the extreme conditions near white holes, allowing scientists to test theories and predict their behavior without the need for physical observation. By combining quantum computing with advanced algorithms, we might unlock new insights into the nature of white holes and their role in the universe. Of course, the journey to understanding white holes won't be without challenges. The sheer scale of the universe means that even if we detect a white hole, it could be millions or even billions of light years away. Overcoming these distances will require not just technological innovation but also international collaboration. Space agencies, research institutions, and private companies will need to work together, pooling resources and expertise to make these ambitious missions a reality. As we look to the future, one thing is clear: the exploration of white holes represents the next frontier in our quest to understand the cosmos. Whether through groundbreaking telescopes, revolutionary propulsion systems, or quantum simulations, the tools we develop will not only bring us closer to solving the mystery of white holes, but also deepen our understanding of the universe itself. And who knows, the answers we find might just change everything we thought we knew about space, time, and existence. As we bring our journey through the 25 space mysteries to a close, one thing stands out above all: the enigma of white holes. These cosmic wonders, though still theoretical, have the potential to completely reshape our understanding of the universe. From their mysterious origins and connection to the Big Bang, to their role in wormholes, multiverse theory, and even the arrow of time, white holes challenge us to think beyond the boundaries of what we know. They remind us that the universe is far stranger and more complex than we can imagine. Throughout this exploration, we've uncovered how white holes could hold the key to solving some of the greatest puzzles in science, from the nature of dark matter to the fate of the universe itself. They've inspired us to dream of futuristic technologies, from advanced telescopes to quantum simulations, that might one day bring us face to face with these elusive phenomena. And while the journey to understanding them is filled with challenges, it's also brimming with possibilities. But the story of white holes isn't just about science. It's about curiosity, imagination, and the human spirit's relentless drive to explore the unknown. It's a reminder that the universe is full of mysteries waiting to be solved, and that each discovery brings us closer to understanding our place in the cosmos. Now it's your turn to join the conversation. What do you think about the mysteries of white holes? Do you believe they exist, or are they just a fascinating theoretical concept? Share your thoughts, theories, and questions in the comments below. Let's keep the discussion going and explore these cosmic enigmas together. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on our deep dives into the wonders of the universe. Until next time, keep looking up. The cosmos has so much more to reveal. Before we wrap up, let's take a moment to dive into some fascinating and lesser-known facts about white holes that will leave you even more intrigued by these cosmic mysteries. Did you know that white holes are often described as the time-reversed versions of black holes? While black holes pull everything in, never letting anything escape, white holes are thought to do the exact opposite. They could theoretically expel matter and energy, but nothing could ever enter them. It's like a cosmic one-way street, but in reverse. Another mind-bending fact is that white holes might not just be theoretical. Some scientists speculate that certain gamma-ray bursts, those incredibly bright flashes of energy observed in distant galaxies, could actually be the signatures of white holes. Imagine that, a fleeting glimpse of a white hole's explosive energy, lighting up the universe for just a few seconds. It's a tantalizing idea that keeps researchers searching for more clues. And here's something truly wild. If white holes do exist, they might not last very long. Some theories suggest that a white hole could collapse almost instantly after forming, turning into a black hole. This means that if we ever hope to observe one, we'd need to be incredibly lucky or have technology advanced enough to catch these cosmic events in real time. Finally, let's not forget the philosophical side of white holes. They challenge our understanding of cause and effect, time, and even the nature of reality itself. What if white holes are gateways to entirely new universes? Or what if they're remnants of a previous cosmic cycle, hinting at a universe that existed before our own? These questions remind us that the universe is full of surprises, and white holes are just one of the many mysteries waiting to be unraveled. So, what do you think about these fun facts? Do they spark your curiosity, or do they leave you with even more questions? Let us know in the comments below. We'd love to hear your thoughts. And if you enjoyed this journey through the enigma of white holes, don't forget to like, subscribe, and hit that notification bell for more cosmic explorations. Until next time, keep wondering, keep exploring, and keep looking up. The universe has so much more to show us. Now that we've explored the fascinating mysteries of white holes, let's shift gears and talk about how you can be part of the exciting world of space research. Believe it or not, you don't need to be a scientist with a lab coat to contribute to our understanding of the cosmos. There are plenty of ways for anyone with curiosity and a bit of time to get involved. One of the easiest ways to dive in is through citizen science projects. These are initiatives where everyday people like you can help scientists analyze data or even make new discoveries. For example, platforms like Zooniverse allow you to classify galaxies, search for exoplanets, or even track asteroids, all from your computer or smartphone. It's a fantastic way to contribute to real scientific research while learning something new. If you're more interested in hands-on activities, consider joining local astronomy clubs or societies. These groups often host stargazing events, workshops, and even collaborative research projects. It's a great way to meet like-minded enthusiasts and learn from experienced astronomers. Plus, you might even get the chance to use telescopes or other equipment you wouldn't have access to on your own. For those who want to take their involvement to the next level, there are educational resources and online courses that can help you build a deeper understanding of space science. Websites like Coursera, edX, and Khan Academy offer free or affordable courses on topics ranging from astrophysics to planetary science. You can learn at your own pace and even earn certifications that could open doors to more advanced opportunities. Another way to contribute is by supporting space research organizations. Many institutions like NASA or the European Space Agency rely on public interest and funding to continue their groundbreaking work. Donations, advocacy, or even spreading awareness about their missions can make a real difference. And who knows, your support might help uncover the next big discovery about white holes or other cosmic phenomena. Finally, don't underestimate the power of curiosity and creativity. Whether it's writing about space, creating art inspired by the cosmos, or simply sharing your passion with others, you're helping to inspire the next generation of explorers. After all, every great discovery starts with someone asking, "What if?" So, what are you waiting for? Whether you're classifying galaxies, attending a stargazing event, or simply learning more about the universe, there's a place for you in the world of space research. The cosmos is vast and there's so much we still don't know, but with your help, we're one step closer to unraveling its secrets. Let's keep exploring.